All right, so today we're on to section 4.3. Just to kind of refresh where we've been and where we're going. We've been looking at methods for statistical inference. We talked about two different methods for statistical inference: confidence intervals and confidence intervals and hypothesis tests. The purpose of a confidence interval is to estimate the value of a parameter. Purpose of a hypothesis test is to assess the evidence for a claim about the population. So hypothesis test is what we've been focusing on here in chapter 4. So thinking about the steps for a statistical test. First, we're going to state the hypotheses. Second, we're going to collect data and calculate the sample statistic. Third, we're going to examine the evidence, and part of that means that we're going to find the p-value. Remember, the p-value is a measure of how much evidence you have against the null hypothesis. The smaller your p-value, the greater the evidence against the null hypothesis. So that's kind of where we left off after section 4.2. But now here we are in section 4.3, and we are going to talk all about step 4, which is drawing conclusions. So we're going to look at this example. I think we talked about this one in general a few lessons ago, but now we're going to come back and kind of analyze the data for it. So it says students were given words to memorize and then randomly assigned to take either a 90-minute nap or a caffeine pill. 2.5 hours later, they were tested on their recall ability. So they were asked how many words they could recall from the list. And we want to know, is sleep or caffeine better for memory? So what do you personally think here? So I'm going to open up the poll. Okay, if you think sleep is better for memory, choose A. And if you think caffeine is better for memory, then choose B. All right, almost everybody chose A for sleep. So that's what I think too. I think sleep would be better. So let's see what they found out in their study, however. So first of all, let's think about what are the cases in this study. So in the chat window, what do you think the cases are in this study? Okay, so the cases were the students. That's who we had participate in this test and who were taking measurements on. Okay, what about the response variable? What would be the response variable for this study? So think about what we're actually measuring here. What did we measure as the response variable? So we are trying to look for better memory and recall ability. But if you remember, they measured that by looking at what? How many words they could recall, right? So the response variable is the number of words recalled. So the response variable, what we actually measured here then would be number of words recalled. So what type of variable rather is the response variable? Is it categorical or quantitative? Quantitative, right? So number of words recalled, it's a number, makes sense to talk about averages, so it's going to be a quantitative variable. Okay, what about our explanatory variable? What would be the explanatory variable in this study? All right, yeah, the
memorization of words.
What? Say it again.
Memorization.
So that's more of our response variable. Our response variable was how many words they were able to recall. But then the treatment, I guess, would be considered the explanatory variable. And the treatment was either sleep or caffeine. So you could call it treatment, or if you said sleep or caffeine, that also works. All right, so is the explanatory variable treatment, is that one categorical or quantitative?
Categorical.
Yeah, that one's categorical. So we have a quantitative response, categorical, explanatory variable. Next question, is this an observational study or an experiment? Okay, good. This one is going to be an experiment because the researchers controlled who got to take a nap and who got the caffeine pill, right? The researchers assigned the students to one of those. The students didn't get to pick which one they wanted to do. The researchers decided randomly who is going to get which one. So that makes it an experiment. All right, so looking at my list here, okay, I can figure out what type of test I'm doing. Okay, and if I look at this, then I can like everything on that row is going to apply to this particular test. And this is based on the explanatory and response and what type of variables that they are. So on my little chart here, we said we had a quantitative response and a categorical explanatory variable. So this last row of my table here is going to show us everything we need. Okay, so this tells me, hey, when I define my parameters, I'm going to have two parameters, mu1 and mu2, or we could call them mu sleep and mu caffeine, whatever we want to call them. Okay, when we write our hypotheses, they're going to look something like this. If I asked what kind of graphs would be good, then it's going to be side by side or stacked histograms, dot plots, or box plots. And if I ask for a sample statistic, okay, there's going to be the notation for my sample statistic. So next, let's talk about writing the hypotheses. So remember, we talked about how we always have two kind of competing, mutually exclusive hypotheses, the null hypothesis and the alternative hypothesis. So the null hypothesis is the claim that's under test, or it's a statement of no effect or no difference. The alternative hypothesis is what we're trying to find evidence for. And I probably shouldn't have put the word claim in there. It's like just what we're trying to find evidence for. The claim is usually the null hypothesis. So we'll not use the word claim in the alternative there. Okay, so let's think about what the hypotheses should be for this test here. Okay, so what should my null hypothesis be? Let's start with that. You can type it in the chat window. Yeah, good. So my null hypothesis, we have two groups that we're comparing. So we're going to have the mean for sleep is equal to the mean for caffeine, or you could use mu1 and mu2 if you wanted to. And then for my alternative hypothesis, remember everything's the same in the null and alternative. The only difference is the symbol that we're using here. So I'm going to still have mu s and mu c. Okay, and what type of symbol should I use here based on the wording of my question? Should I go with greater than, less than, or not equal to? All right, yeah, I'm going to go with not equals. And the reason why we're choosing not equals is because we wanted to know, is sleep or caffeine better? So we weren't leaning one direction to start with or anything, or the researchers weren't who wrote this question before we collected any data. We just wanted to know which one is better. So either way, we want to know if sleep is better or we want to know if caffeine is better. So we're going to use not equals to for the alternative there. All right, once we've written our hypotheses, the next step is to collect the data and compute the sample statistic. So what's the notation for the single sample statistic that we're going to use for this hypothesis test? All right, so think back to the table that we had. Remember, it had sample statistic notation on that. So we're going to use x bar 1 minus x bar 2, which we called it x bar s and x bar c. So we'll call it that, even though that looks like a money sign now. So we're going to use x bar s minus x bar c. Okay, and what kind of values of this sample statistic will support the alternative hypothesis? So I'll throw up the poll for this one. Whoops, let me relaunch the poll. That's what I want to do. Okay, so if you think negative values support the alternative, choose A. If you think positive values support the alternative, or if you just think values different from 0 support the alternative, you can put your choice in the poll. All right, most people put the answer C, which is correct. So values different from 0 would support the alternative. Remember, our alternative hypothesis was mu s not equal to mu c. So if I compute my sample statistic here and get a negative value, that means that the sleep was less and caffeine was more. So that would show that caffeine was more, but it would show that they were different, right? And a positive value would also show a difference, only it would show that sleep is more and caffeine is less. And we wanted to know either way, caffeine or sleep being more. So any values different from 0 would be in support of the alternative hypothesis. So to find the actual sample statistic here, we're going to use StatKey. If you want, you can do this with me. Let's see, come over here to this screen. So I'm going to come in here to StatKey, and we're going to be looking at a randomization hypothesis test. Okay, remember that I can look over here in the first column and see, okay, well, what kind of variables did I have? How many and what type? And once I locate that, I can follow that over. So in this case, we had one quantitative, one categorical. I can follow that over and say, okay, I'm doing a test for a difference in means. Also, by this point, we've written our hypotheses. So we should be able to see, hey, I'm doing a test for a difference in means. I know what that looks like. So if I come in here, this is actually one of the data sets that's already loaded in here. So you can find it in the drop-down menu. It's called Sleep Caffeine Words. So it's like the fourth one down on the drop-down menu. And remember, you can always find the value of the original sample statistic in the upper right-hand corner. So up here, it tells me that X bar 1 minus X bar 2 was equal to 3. So sleep minus caffeine, mean for sleep minus mean for caffeine in our sample was equal to 3. So that's what I'm going to put for my sample statistic here. So up here, that was equal to 3. Am I sharing the right window with you guys? I switched to sharing this one, right? I don't know. Zoom's not really liking me today. Guess we're back on the outs again. It was like giving me some warning. Anyway. All right, so now we have our sample statistic, a 3. So that tells us that in our sample, sleep was bigger than caffeine because I got a positive number, right? If I get a positive difference, that meant sleep was higher. If I got a negative difference, that would mean that the caffeine was higher. But we have to figure out, well, you know, what kind of a value is 3? How much evidence is that there? So next, we're going to examine the evidence. We want to compare our sample statistic 3 to the value claimed under the null hypothesis, which is 0. Okay, the further apart they are, the stronger the evidence for the alternative hypothesis. So recall, and I put a spot in your notes for you to write down these definitions again, so you can write them down if you want to. We did write them down last time too, though. P-value is a probability computed assuming the null hypothesis is true, that the observed statistic would take a value that is as extreme or more extreme than that actually observed. All right, and then remember, we've also been talking about how the smaller the p-value, the stronger the evidence against the null hypothesis and in favor of the alternative hypothesis. Okay, remember the null and alternative hypothesis, like there's no overlap between those two. They're mutually exclusive, like they are competing against each other. So evidence against one would be in favor of the other one. So evidence against the null hypothesis is also evidence in favor of the alternative hypothesis. And then remember, just kind of remembering how to find a p-value. Again, this is review, but I did put a little spot on your notes for you to write it down. Again, just as a reminder. So you're going to construct the appropriate randomization distribution, find the sample statistic on your randomization distribution, use that to determine the tail proportion. And then if your test is one-sided, then the p-value will be equal to the tail proportion. And if your test is two-sided, your p-value will be equal to 2 times the tail proportion. So these are kind of general instructions. These work whether you're using StatKey or whether you're kind of given already the randomization distribution. The process is essentially the same, except in one case, you're counting all the dots. And in the other case, then StatKey is counting all the dots for you. So let's go back to StatKey. and we're going to do that here. So first, we're going to construct a randomization distribution. So I'm going to generate some samples here. Okay, I'll do like, I don't know, 4,000, 5,000. I'll do 5,000. Sounds like a good number. Okay, this was a two-sided test, so I'm going to click on two-tail. And now I need to, and this is important, a lot of people forget this too, I need to enter the value of my original sample statistics. Remember, my original sample statistic was 3. So looking down here, 3 would fall on the right side of this graph. So I'm going to use the right box down here. I'm going to put in the number 3 and hit OK. All right, and my floating box says 0.024. So my p-value here is going to be double the tail proportion. So I can either double that number or add those two numbers together. It's the same thing. So I'm going to get 0.048 for my p-value. All right, and if you're doing this along with me, you could have ended up with numbers that are slightly different than my numbers, because anytime we do any of these resampling techniques like randomization distributions or bootstrap distributions, then you get a slightly different answer every time. But you should get something that's really close to my answer here. All right, so now I have my p-value. Okay, so this tells me that if there really is no difference on number of words recall, whether you have sleep or a caffeine pill, if there really is no difference, the probability that I would take a sample and see a sample difference of 3 or more is 0.048. Okay, and we also said the smaller your p-value, the stronger the evidence against the null hypothesis. All right. So now we're ready to start talking about drawing conclusions. Okay, so we have this p-value, we have this measure of how much evidence we have. Now we have to use that evidence to make a decision, to draw a conclusion. And our hypothesis test conclusions are always going to be made up of 2 parts. So the first part is going to be a formal decision. Okay, we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. So part 1 is a formal conclusion or formal decision, I'll call it. So the formal decision, we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. Okay, instead of failing to reject, you could also use the phrase do not reject. The textbook uses do not reject, but most textbooks that I've worked with use fail to reject. They mean the same thing, so you can use either one, it doesn't matter. All right, so part 1 of our conclusion is going to be this formal decision. We're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. Okay, step 2 or part 2 of our conclusion is going to be a conclusion in context about the alternative hypothesis. Okay, remember when we defined the alternative hypothesis, we said, hey, this is what we're trying to prove or find evidence for. So when we come down to writing our conclusion, we want to know, hey, did we find evidence for this alternative hypothesis? What does that mean? Did we not find evidence? What does that mean? So that's where this conclusion in context about the alternative hypothesis is going to come in. Okay, so our entire hypothesis test conclusion has to have both these parts: rejecting or failing to reject the null hypothesis, and then the conclusion in context about the alternative hypothesis. So let's talk about each of these different parts and how we write those. So hopefully you guys got those written down. All right, so first, let's talk about our formal decision. Okay, so the formal decision is this part 1. Okay, and we said that basically there's 2 options for this formal decision. Okay, the first option is the p-value is small, so we reject the null hypothesis. So that's one possible conclusion. So possible conclusion number one is if the p-value is small, then we're going to reject the null hypothesis. Okay, and the other possible conclusion that we could be making here is if the p-value is not small, then we're going to fail to reject the null hypothesis. All right, so if the p-value is not small, then we're going to say fail to reject or do not reject. Either one of those phrases is fine. The null hypothesis. Okay, so notice that the formal decision here is all based on the null hypothesis. Well, it's using the p-value, but it's kind of about the null hypothesis. We're either rejecting the null hypothesis or we are failing to reject the null hypothesis based on the size of our p-value. All right, so here's an example. This one's a test they did of row correlation to see if the correlation was positive, and our sample statistic was 0.6. Okay, so based on this randomization distribution, then do you think that is the p-value small? Do you think we should reject the null hypothesis, or is the p-value big and we should fail to reject? So you can put your answer in the poll. So A, if you think we should reject the null hypothesis because the p-value would be small for this, or B, if you think that the p-value is not small, so we should fail to reject. All right, a few mixed results here in our poll. So let's look at this. So our original sample statistic is R equals 0.6. So if this is my randomization distribution, then I'm going to look on the x-axis for 0.6. Here it is, and draw a line. Okay, and see, I only have one dot over here. That is, unless I have, nope, nothing's hiding. That is more extreme than 0.6. So my p-value is going to be really, really small. I don't know exactly how many dots there are. It kind of looks like 1,000. So it might be about 1 in 1,000, which would be a p-value of 0.001. So 0.001, that seems like a pretty small p-value. The smaller your p-value, the greater the evidence against the null hypothesis. Small p-value means reject the null hypothesis. So I would say, yes, we should reject the null hypothesis here.
I have a
Okay.
question.
Yeah.
So for the conclusion, let's say that we got like a 1 or a 2, then we would fail to reject the.
Hold on to your question for a couple of minutes.
Okay.
I promise we're getting there. Okay, so here's another example. So here I have a sample statistic of 0.1. Okay, so I'm going to relaunch that poll. And this time, tell me, what do you think? Based on this randomization distribution and this sample statistic here, do you think we should reject the null hypothesis? So do you think p-value small, reject, or p-value not small, do not reject? You guys are a lot faster to answer this time. All right. Here's the results. Most people chose B, which I think is a good choice for this one. So here, I'm going to find that original sample statistic on there, 0.1. That's way over here. You can see there's a whole bunch of dots. I can't even count that high. Looks like there's probably 335 because they tell us the p-value up here is 0.335. So that seems like a pretty big p-value. Big p-value means do not reject, right? So far we had really tiny p-value. Clearly we reject. Here we've got pretty big p-value. Clearly do not reject. Okay. Here's another one. What if our R was 0.336? Then what do you think about this one? Do you think that our p-value is small, reject, or not small, fail to reject? All right, we got kind of mixed results on this one. Almost, not quite, but almost evenly split here. If I look at 0.336 on my x-axis here, then it's about right there. So I end up with a p-value of 0.05. So about half of you said, sure, let's reject. And the other half of you are like, I don't know, maybe we shouldn't reject. So that kind of brings up the question that Bo was asking is that, okay, like here, this one was easy, clearly do not reject, right? This one was easy, clearly reject, but where do we draw the line? So this one's, you know, a p-value of 0.05, like, is that small enough? How small is going to be a small enough p-value that we're going to want to reject? And so we said, hey, you know, p-value is small, reject, p-value is not small, do not reject. But again, how small is small? How do we decide how small is? The answer is that it kind of depends a little bit. Okay, it's not like a hard and fast rule that we're going to talk about, but there has to be a point where we make a decision, where there's some number where we're like, okay, if it's lower than this, that's it. You know, that's my cutoff point. Then I'm going to reject. Okay, or if it's bigger than this number, then I'm going to be like, okay, fine, I'm going to fail to reject. And so that decision point, kind of that cutoff value, is something that we call the significance level. So let's write down some things about the significance level. So first of all, the significance level, which has the notation of the Greek letter alpha. Okay, so you might want to write that on your notes. I don't have like a specific space to write it, but like next to where it says significance level, you could write the Greek letter alpha, which looks kind of like a fish, kind of like a Jesus fish, like you see on the back of people's cars. Like, I don't know if that's an appropriate thing to say in class or not, but that's kind of basically what it looks like. So, or like if you were trying to draw a goldfish and you were back in like kindergarten, or this is still how I draw goldfishes when I'm an adult, then it kind of looks like an alpha. Okay, so this is the decision point for the p-value. Okay, so this is kind of like our cutoff. This is where we're, you know, this is our line in the sand right here, so to speak. Okay, so if the p-value is less than alpha, then we're going to reject the null hypothesis. Okay, so if the p-value is less than this significance level, this alpha value, then we're going to reject. And if the p-value is greater than alpha, we're going to fail to reject the null hypothesis. Okay, and so some common values that are typically used for alpha are going to be 0.10, 0.05, and 0.01. So these are kind of like the standard, like almost all tests use one of these three significance levels here. And you can think about like significance levels in hypothesis tests are a similar idea to confidence levels in a confidence interval. Okay, so basically we're going to choose our significance level based on how willing we are to be wrong. Okay, so remember when we talked about confidence intervals, we said, you know, that a 99% confidence interval, 99% of the time, it's going to contain our true value. But the trade-off is we had to have a little bit wider of an interval if we were going to do a 99% confidence interval versus, say, a 90% confidence interval. And it's kind of the same thing here. We're going to choose our alpha level here, our significance level. If I choose a higher one, like 0.10, then I'm going to have an easier time rejecting the null hypothesis. But at the same time, I'm going to be more likely to make a mistake, like reject when really I should not have rejected. So we're going to talk about that a little bit more in section 4.4 next time, kind of that trade-off there. Okay, but for now, just know that these are the common levels. And I'm also going to add to that if there's not a level given to you, then use 0.05. So 0.05 is kind of like everybody uses 0.05 unless otherwise specified. So sometimes we might use one of these other ones instead, but 0.05 is kind of the standard, I guess. All right, and kind of another term that we're going to see there, if the p-value is less than alpha, then we're going to say that the test is statistically significant. Okay, it's okay to use that phrase. So if the p-value is less than alpha, we say that the test is statistically significant. All right, so we just said that, hey, if our p-value is less than alpha, we're going to reject the null hypothesis. If our p-value is greater than alpha, we're going to fail to reject. So this is my memory trick that I use to help me remember which way to draw the conclusion. I always say if p is low, meaning lower than alpha, then HO must go. And if p is high, meaning higher than alpha, then we're going to keep the guy. So if p is low, HO must go. And if p is high, keep the guy. So you can, there's a spot on your notes if you want to write down my memory trick for that. Then let's talk just a little bit more about this idea of statistical significance and how that's going to apply to our test here. So when we think about this idea of being statistically significant, okay, first of all, we said we're going to call something statistically significant, a test statistically significant, or we might say the results are statistically significant if the p-value is less than alpha. So statistically significant if the p-value, so it kind of means that the p-value is less than alpha, our significance level. Okay, and if the p-value is low, if it's less than alpha, that also means that the results were unlikely to occur due to chance. So being statistically significant also means unlikely to occur due to chance. All right, and a lot of times in the literature, and I wrote this in your notes already if you have it written down, so you wouldn't need to rewrite it or anything. But basically, you'll see things like the data was significant at the 0.01 level, or this study was significant at the 0.01, 0.05 level. Basically, what they're doing when they say something like that is, remember those three main significance levels that we use, the 0.10, the 0.05, and the 0.01. They're choosing the smallest one that their p-value was less than, and then they're going to say their data was significant at that level. So that can give you a clue of kind of what type of p-value they have too, because they always want to make, and anytime you're reading something in the literature, they want to make their results look the best that they possibly can. So for example, if they end up with a p-value that is like, let's say they have a p-value of 0.07, okay? So then if I think about my main alpha levels, 0.10, 0.05, 0.01, okay, this one is only less than 0.10. So I would say that my results are statistically significant at the 0.10 level. Okay, and if I'm reading this, okay, what I know is if they tell me it's significant at the 0.10 level, I know that my p-value had to have been between 0.10 and 0.05, because if I would have had a p-value that was smaller than 0.05, like let's say 0.03, then I would have said it's significant at the 0.05 level, okay? Because I always want to choose the smallest one, because the smaller your p-value, the more significant the evidence, okay? So we want to be like, we want to show that we have as much evidence as possible. So we're going to choose the smallest one that this is less than. So if I have 0.03, then I would say it's significant at the 0.05 level, even though that would also mean that it's significant at the 0.10 level, but I want to choose the one that makes me look the best, if that makes sense. There's another activity, I can kind of explain this a little bit, like that I do if I'm in the classroom, that's kind of fun, is I'll take a deck of cards that I've actually combined two decks, and I've taken all the black cards and put them together in one deck, so it looks like just one deck of cards. And I'll bring a bag of candy and I'll say, hey, let's play a game. Like the first person to be able to draw a red card, gets this whole bag of candy. And so I'll fan out the cards and I'll walk around the room and say, okay, who wants to play? And so people always want to play, and they'll pull out a card, and the first person gets a black card, and everybody's like, oh dang, and then I'm like, okay, well let's try somebody else. The second person gets a black card, and they're like, oh, darn it. And then, they keep wanting to try. And usually right about the time I get to the fourth or fifth person, that's when somebody raises their hand and they're like, hey, I don't think there's actually any red cards in your deck. Like, I think you rigged the deck over there. And because that's about the point naturally that we're like, okay, this is unusual. Like, it would be totally normal to get the first black card, right? And even the second black card and the third black card. But by the time we're getting to like the fifth black card in a row, it's unlikely that would come from a regular deck that has both black and red cards. So that's kind of where our natural, like, something's off meter kind of sparks up. And that's kind of why we use 0.05 a lot for doing these significance tests, because that's kind of our, hey, yeah, I don't think that would really happen due to chance kind of mode. Okay, we talked about statistical significance. Okay, so now we've talked about the first part of our conclusion, which is either rejecting or failing to reject the null hypothesis. Okay, now we're going to talk about the second part of our conclusion, which is going to be the conclusion in context about the alternative hypothesis. And it basically boils down to what we decided in our part one. So if in part one, we decided to reject, then what that means is that we have sufficient evidence for the alternative hypothesis. So write this down where it says conclusion step 2, conclusion in context about the alternative. Okay, so if we reject H naught, then we have sufficient evidence for the alternative. Okay, and if we do not reject H naught, so if in part one we don't reject, that means that we do not have sufficient evidence for the alternative. Okay, so notice that either way, whether we reject or not reject in part one, our conclusion in context is going to be about the alternative hypothesis. So the bulk, this is going to be like the most wordy part of our conclusion. The first part is pretty short. It's like reject H naught, do not reject H naught. But the second part here, it's going to have lots of words in it, okay? Because we're basically going to be writing out that alternative hypothesis in words every time. And it's going to be about the alternative regardless of what we chose in the first one. So if we chose reject in the first one, we're going to say, hey, we can reject the null hypothesis. That means that we can conclude that the alternative is true. Or if we fail to reject, then we do not have evidence for the alternative. So there's a nice little flow chart here that kind of shows us how this goes. So if the p-value is less than alpha, that means our formal conclusion is going to be reject the null hypothesis. And when we write out our conclusion in context, it's going to say this. We're going to say we have sufficient evidence that, and then you're going to write out the whole alternative hypothesis in words. If our p-value is greater than or equal to alpha, that means our formal conclusion is going to be fail to reject or do not reject the null hypothesis. And our conclusion in context is going to say we do not have sufficient evidence that, and then again, we're going to write out our whole alternative hypothesis in words. So the part one, based on the null hypothesis, part two is all about the alternative hypothesis. So here's our tea versus coffee example here. Oh, this is tea versus coffee. We switched away from sleep versus caffeine. I don't know why we did that. Okay, just for funsies, I guess we did. We went back to talking about tea and coffee. This is one we talked about last time where they were trying to see whether tea or coffee had the higher immune system response. So if you remember from that example, we ended up with a p-value of 0.026. Okay, so if we are using an alpha level of 0.05, a significance level of 0.05, then 0.026 would be less than 0.05. So we would reject the null hypothesis. And if we're rejecting the null hypothesis, that means we have sufficient evidence that, and now I'm going to write out the whole alternative hypothesis in words. So we have sufficient evidence that the mean immune response for people who drink tea is higher than the mean immune response for people who drink coffee. So let's look back, and in your notes, you probably have to flip back to the very front page of your notes for the sleep versus caffeine example. Here, okay, and what kind of p-value did we get for this one? I got 0.048, I think. Did you guys, anybody do it on StatKey as well and get something?
0.05.
You got 0.05?
Close.
Okay, so let's use my p-value. That's a little bit more straightforward. So my p-value is 0.048. Okay, so first part of my conclusion, should I reject or fail to reject?
Reject.
Okay, reject, because 0.048 is less than 0.05, right? And if they don't specifically tell us an alpha level to use, we're going to do that. So I'm going to reject. Okay, and if you look back at your alternative, or look back at your hypotheses. So our hypotheses were null hypothesis, mu S equals mu C, and alternative hypothesis, mu S not equal to mu C. Okay, so if I'm rejecting, so I like to draw a line through it. It makes me feel like I'm really rejecting it. Then I'm going to say that I have sufficient evidence that the alternative is true. Only I'm in context, I need to write it all out. So let me put this up here. So first of all, I'm going to say we reject H naught. Okay, that's part one. Okay, the second part, it's okay to use the symbol H naught in the first part, but for the second part, it's not okay to use the symbol HA in the second part. We want this in the context of the problem. So we're going to say we have sufficient evidence that the mean words recalled for people who get sleep is different from the mean words recalled for people who take caffeine pills. All right, so if you look at my wording here, I've basically just followed my alternative hypothesis exactly. So my alternative hypothesis was mu S not equal to mu C. So if you've defined mu S and mu C somewhere, you're just plugging in those words you use to define those and throwing in a word for the not equals, like not equals or different from or whatever. Okay, and we have sufficient evidence. So remember, rejecting goes with sufficient evidence. So we have sufficient evidence that the mean words recalled for people who get sleep is different from the mean words recalled for people who take caffeine pills. Now, in this particular experiment, we actually, the data itself showed us that the people who got sleep recalled more than the people who took caffeine pills, right? So because the data showed me the direction of the difference, it would also be okay for me to say more than here or greater than or something like that. Okay. You could still say different from, it's still okay to say different from, but like kind of writing conclusions 2.0. If I look at the data, once I've collected the data, then I know the direction of the difference, if there is one. And my data showed, hey, they're different. And by the way, sleep is better than caffeine. Okay, so I could also work that into my conclusion here. Okay, so I'm going to back this up a little bit just to show you a couple other examples here. Okay, thinking back to my free throw example, null hypothesis was that I was an 80% free throw shooter. The alternative hypothesis, what you guys were trying to prove, is that I was less than an 80% free throw shooter, and my p-value was 0.001, or let's say my p-value was 0.001. I didn't actually do this test. But if that was the case, then you would say we reject H naught. We have you could still use the word sufficient here. If you have a really small p-value, it's okay to throw in other words like strong or or something like that. So we have strong evidence that Professor Wilkinson's free throw percentage is less than 80%. Okay, so see how I'm just taking that alternative hypothesis and writing it out in words right here. Okay, here's another example. Thinking about Pizza Hut delivery times. Null hypothesis was that the mean pizza delivery time was less than or equal to 30 minutes. Alternative was that it was greater than 30 minutes. So let's say we did a test and we got a p-value of 0.35. How would we write that conclusion? Well, 0.35 is high, much higher than 0.05. So we would keep the guy. In other words, we would fail to reject, or do not reject. So we do not reject the null hypothesis. We do not have sufficient evidence that and then look, I'm just writing out this alternative hypothesis in words here, that the mean Pizza Hut delivery time is greater than 30 minutes. All right, so you can kind of follow this basic pattern for writing these conclusions. Okay, so first caution, do not reject H naught is not the same as accepting, and we are never, ever, ever going to accept. So we never say that the null hypothesis is true, no matter what your p-value is. I don't care how big your p-value is, you're never going to say that the null hypothesis is true. So you can't ever prove the null hypothesis. The only one that you're trying to prove is the alternative hypothesis. Okay, so lack of evidence against the null hypothesis is not the same thing as evidence for the null hypothesis. So here's an example. Let's say we are trying to figure out if this animal X is an elephant or not. Okay, so null hypothesis is that the animal equals an elephant. So the animal is an elephant. And the alternative hypothesis is that the animal is not an elephant. So what kind of conclusion would you get if you got the following data? Okay, so if we found out that this mystery animal walks on 2 legs, okay, then that seems like it would be evidence that in favor of the alternative, right? That X is not an elephant because elephants don't really walk on 2 legs, right? So we might reject and say that, X is not an elephant, right? Although can't be certain because we have some lovely circus elephants that actually can walk on 2 legs. Okay, but what if the evidence we have is that animal X has 4 legs? Well, so we don't have enough evidence to reject. We don't have any evidence in favor of the alternative, but can we conclude that X is an elephant? No, because there's lots of other animals that also have 4 legs. So we have some, so we never, ever, ever are going to say that the null hypothesis is true because maybe we just don't have enough evidence to say it's false, basically. So, okay, the next caution here is that there's no sharp boundary between significant and not significant. Only increasingly strong evidence as the p-value gets smaller. All right, so if we think about this, we said the smaller your p-value, the stronger the evidence against the null hypothesis. But, how much difference is there really between a p-value of 0.049 and a p-value of 0.051 in terms of the amount of evidence that we have? Well, there's really practically no difference between those 2 p-values. And yet if our significance level was 0.05, one of those we'd end up rejecting and the other one we'd end up failing to reject. So there's not really like some like black and white, like, ooh, significant, ooh, not significant. Really just we have stronger and stronger evidence as the p-value gets smaller. But as we said before, we kind of need to have some kind of line in the sand somewhere where we start making these reject, fail to reject type decisions. Okay, and that's why we have to have these significance levels. So how do we choose our significance level? Well, it kind of just depends on how willing we are to be wrong. And we'll talk about this more in section 4.4 that we're going to cover next time, like how to decide what level of alpha to choose. Okay, so this picture kind of shows although we're kind of making black and white decisions with our alpha level, reject, fail to reject, really, when we think about our p-value, it's on more of a, a gradient scale here, where the smaller your p-value, the stronger the evidence that we have. It's not really as black and white as it makes it seem with our significance level. So in order, how we're going to decide is we're going to ask what kind of the consequences there are for making the wrong decision. So in other words, rejecting the null hypothesis when in reality the null hypothesis is really true, or failing to reject the null hypothesis when in fact the null hypothesis is actually false. So next time we're going to talk about the two different types of errors that you can make when you do a hypothesis test, and we're going to talk about looking at how to decide which type of error is worse, okay, and choosing a level of significance based on how bad it would be to make each type of error. So that's kind of a preview of coming attractions here. All right, let me look at the time. Okay, I have another example that I think we'll kind of walk through together, and then I'm going to put you into your groups and you're going to do another big example. So kind of start to finish on a hypothesis test. So now we've learned everything. So we've learned how to state the hypotheses. We know how to collect the data, calculate the sample statistic. We know how to examine the evidence by finding the p-value. And now we know how to draw conclusions using the p-value. And we recognize that conclusions have these two parts, rejecting or failing to reject the null hypothesis, and then conclusion and context referring to the alternative hypothesis. So this example that we're going to walk through was a study that they did on hormone replacement therapy. So until 2002, hormone replacement therapy with estrogen and or progesterone was commonly prescribed to postmenopausal women. And then it actually changed based on the results of this study that we're going to look at. So that in this study, they had 8,506 women who were randomly assigned to take the hormone replacement therapy, and then another 8,102 that were randomized to take a placebo. So they took all 16,000 plus of these women, randomly assigned them to these two different groups, the hormone replacement therapy and the placebo. And in the hormone replacement therapy group, 166 developed invasive breast cancer. And in the placebo group, 124 developed invasive breast cancer. So these are small numbers. This is a huge, huge sample size. Usually we don't see sample sizes this big. But what they were trying to figure out by doing this study is, does taking this hormone replacement therapy, does it increase your risk of getting breast cancer? Because obviously that would be bad. Okay, so the cases here, what are going to be the cases? I'll back up one.
The woman in the experiment.
Yeah, the women in the experiment, exactly. So it was something like 16,500 something or 600 something. So it was 16,000 plus women. All these women were the cases. Okay, then our explanatory variable is the treatment. So whether they got the hormone replacement therapy or, oh, thanks, Jolie added it up for us. So the 16,608 women in the study here. Our explanatory variable was either the hormone replacement therapy or the placebo, so what treatment they got. And then the response variable was occurrence of breast cancer during the study. So based on what our explanatory and response variables are, which one of these scenarios down here are we working with? What type of test are we doing? What do we got here?
Two categorical. Oh.
Yeah, the treatment here, it's going to be categorical, right? Hormone replacement therapy or placebo. Occurrence of breast cancer, that's like a yes, no kind of thing. So that's also categorical. So I can see that I'm working with two categorical variables, which means everything's going to come off of this row here on my chart. So I'm comparing two population proportions here. My sample statistic is going to be the difference in the sample proportions. Shows how I'd write my hypotheses, everything else. Okay, so for my my parameters. First one, P1 would be the proportion of women taking the hormone replacement therapy who get invasive breast cancer. And if you want, you don't have to use 1 and 2. You could use like H for HRT and P for placebo. So either one. So my presentation uses 1 and 2. So P1, proportion of women taking the hormone replacement therapy who get cancer, breast cancer. And then P2 would be the proportion of women not taking the hormone replacement therapy, so taking the placebo, who get invasive breast cancer. So my null hypothesis is always going to have the equal sign in it, and I'm comparing two groups. So then it's pretty easy to write the null hypothesis for two groups because we're just going to say that the two groups are equal. P1 equals P2. Okay, but what about my alternative hypothesis? What kind of symbol should I use in my alternative hypothesis?
P1 is greater than P2?
Okay, why greater than?
Because it's the question asks us if HRT increases the risk of breast cancer.
Right, so we got this keyword increase right here. So increase is code word for greater than. So my alternative hypothesis then would be that P1 greater than P2. So we think the people on the hormone replacement therapy are going to have a higher incidence of the breast cancer. So there's my hypotheses. Okay, so next I want to look at my sample statistic. Okay, so to calculate my sample statistic, they told me in the hormone replacement group, 166 out of 8,506 developed breast cancer. In the placebo group, 124 out of 8,102 developed the breast cancer. So, so I could figure out these proportions. So P hat 1 would be the 166 over 8506. P hat 2 would be the 124 over 8102. And if I divide each of those and then subtract, that tells me the difference, P hat 1 minus P hat 2, which is equal to 0.0042. So this is my sample statistic here, my best estimate, this 0.0042, which seems like a really, really, really small number, right? It seems pretty small difference in the two groups. But remember too, that we had huge, huge sample sizes here, really big sample sizes. All right, so once I find my sample statistic, then I'm going to find my p-value. So we could go to StatKey and plug those numbers in to try to get a distribution, but I actually have a chart here for this one. So we're going to do this one kind of by hand so we can practice doing it this way. So remember, okay, that I'm going to look for the value of my original sample statistic along the x-axis. So my original sample statistic is 0.0042. So here's my randomization distribution. I'm looking for 0.0042. Okay, so my original sample statistic would be about right here. So the line here is 0.004, so 0.0042 would be pretty much right next to that. Okay, so then I'm going to draw a line here and I'm going to count these dots here. So I'm going to count everything that is as extreme or more extreme. So if you have values that fall like right on the line, you count those too. Okay, so because that would be the as extreme part. So counting these, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And actually there was one that I missed because all your pretty pictures were on top of it. Okay, so include that in your little circle, 20. So it looks like I have 20 dots. Okay, so in order to figure out the tail proportion, I take the number of extreme dots, I should say that, extreme dots, and I'm going to divide it by the number of samples, which is the total number of dots. So in this case, I got 20 dots. I can see that my number of samples up here is 1,000. So 20 divided by 1,000 is 0.02. All right, and this is my tail proportion. Did I have a one-sided or a two-sided test? One-sided. How did I know it was one-sided?
Because they asked does a HRT increase risk of breast cancer? So
Yeah, so I ended up with a greater than, right? So if my alternative hypothesis has greater than or less than, it's a one-sided test. If it has not equals to, it's a two-sided test. So this was a one-sided test. In a one-sided test, the p-value equals the tail proportion. So in this case, my p-value will just be equal to 0.02. Okay, so I have a p-value of 0.02. So if I use an alpha of 0.05, kind of our standard alpha value, then should I reject or fail to reject the null hypothesis?
Reject.
Reject, right. So I reject the null hypothesis. When I reject, that means that I have sufficient evidence, or use the term convincing here, that the proportion of people who take the hormone replacement who get cancer is greater than people who do not take the hormone replacement getting cancer. So in a little simplified terms, I have it written here, but if you want to stick with just writing out exactly in words what all that stuff is, that might be your best bet until you get more comfortable with it. So in other words, they did have convincing evidence that the hormone replacement therapy increased the risk of breast cancer. So can we say that the hormone replacement therapy was causing the increase in the breast cancer things based on this study? Can we show a cause and effect relationship here?
Yes, because it was an experiment.
Yes, because it was an experiment. Exactly. So we know that the cause actually was that hormone replacement therapy. So because of the results of this study that they did, they actually terminated the trial right then a little bit early, and they no longer routinely recommend the hormone replacement therapy because it does increase your risk of breast cancer.